Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Underground Stormwater Storage for Detention or Reuse. My name is Amanda and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them, their cultures and to elders past and present. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, ECHO. ECHO in Australia offers an extensive portfolio of stormwater, building drainage systems, cable pit and ducting systems, access covers and other niche products. ECHO take pride in providing excellent customer service and extensive technical support from specification through to the finished product installation. Today, we will hear from two speakers, followed by our live audience Q&A. And as always, I encourage you to send questions through to our speakers via the chat box. I'd now like to welcome our first speaker, Darren Chan. Darren is the brand manager at ECHO for civil construction products and the NATA authorised representative for ECHO's testing laboratory. ECHO continue to support engineers and designers with innovative products and free online design tools. Please welcome Darren Chan.
Thanks, Amanda. Hi everyone, and welcome to our presentation on underground stormwater storage for detention or reuse. Before I start, I want to thank Amanda and the EA team for their help in making today's webinar possible, and to Mark for presenting with us. Over the next 25 minutes or so, I'm going to describe the role of geocellular underground plastic storage tanks, their characteristics, and offer you a guide on how to specify them. Underground tanks are used in lots of projects as councils legislate to protect their downstream waterways and infrastructure. Managing both the quantity and quality of water being discharged off a site is only going to grow in importance, particularly as our cities urbanise and rainfall events intensify as the climate changes. These days, larger areas of the built environment are being covered by impermeable surfaces, which of course increases the risk of flooding. Tank solutions are a conventional way to store and slow down the surface water runoff to pre-development rates as well as replenish the groundwater at a more natural rate. These are the system elements that are designed to work with the natural water cycle. On a slab or pavement, drains are typically positioned to intercept or collect stormwater runoff, which is then treated or cleaned to prevent clogging or contamination downstream. As you can see on the image, there are a number of tank solutions available to engineers and urban designers, both natural or engineered structures. Some of the engineered tank solutions include cast-in-place, precast concrete tanks, arches, and plastic structures. We'll focus today on just plastic stormwater tanks, which can be easily integrated in a stormwater management plan for the infiltration, retention, or detention of surface water runoff. Detention systems, also known as attenuation systems, are designed to spread the peak flow of a storm event. It does this by holding and releasing stormwater slowly. As I mentioned before, the idea of this is by controlling the runoff to reduce the risk of flooding downstream from a development. A retention system collects and stores water permanently for reuse, for example, to water landscape areas or for firefighting purposes. Infiltration systems or soak wells are used a lot in sandy areas to temporarily store water to allow it to naturally seep back into the ground to replenish a dropping water table. To illustrate this, retention and infiltration are two common adaptations of these tanks to make the best use of captured stormwater. Retention is for irrigation or reuse purposes. Infiltration is where the soil can naturally free the water from impurities. In both cases, the water is used at or close to the source of collection without it flowing through to any downstream infrastructure or receiving waterways. But if discharging into downstream infrastructure is the objective, then as I explained before, detention gives designers the greatest control over the quantity of water to enter it. In very simple terms, it's an easy calculation. Before I go on, I want to make special mention on two types of hydraulic control structures. The first are stormwater treatment devices. These are located upstream of the tank, with their performance being individually assessed and governed by the EPA and local DA requirements. And depending on the project requirements, there are many types, from gross pollutants or silt traps, stormwater filters, permeable pipes, to even light oil separators used where hydrocarbons exist. The other type of hydraulic structure are flow control devices, which, as the name suggests, control the release of water to prescribed rates downstream of the tank. These are typically installed in chambers with either purpose-designed mechanisms or just a conventional orifice plate. Now, both these hydraulic control structures are not the topic of today's presentation. I wanted to mention them as they are essential elements that affect the quality and quantity of water being discharged off the site. I want to go back to this slide to give an overview of the storage options available. From the top, we've got a detention basin. You often see these used in low to medium density areas. They tend to take up space that could otherwise be used for urban or commercial development. Then next are concrete tanks, normally expensive to construct and transport. Next along are the plastic arch systems, which require a decent amount of space. And finally, plastic tanks. And within this large category, there's a huge range of options, with not all being equal. So today, I'm only going to focus on plastic tanks that can be assembled into producing underground cells for water storage. These can be adapted in a softscape where infiltration can be achieved. Here you can see them assembled, wrapped, and backfilled. They can be installed under slabs in commercial and industrial applications where space is a premium. In fact, geocellular plastic tanks are installed in lots of projects, from car parks, driveways, and in landscaped areas to commercial buildings, schools, industrial areas, airports, and military bases. Here is an example of a recent installation of a tank being used for infiltration at a life-saving club. Stormwater captured from the club's rooftop and its infiltration into nearby vegetation was part of the sustainability design brief. With limited space to work with, designers needed to maximize the storage capacity of an infiltration tank whilst fitting into a very restricted space. An easy-to-maintain sedimentation trap was also required. This is an example of a tank being used for detention in Griffith, New South Wales. Designers had to deal with runoff from the site. The tank would store and gradually release the stormwater runoff into the council's downstream infrastructure, while also allowing direct access for watering the sports field. In the industry, there is a wide range of plastic tanks. The two on the right are typical of plastic crates. The one on the left is typical of a modern geocellular unit. Unlike concrete tanks, plastic tanks are versatile. They can be cut and joined, and the structure can be used for infiltration. Good designs have a high void ratio and easily maintained. Good designs are also load rated and hold their strength over time, but there are poorly designed plastic tanks that are difficult to access, inspect, and maintain. Unfortunately, these give all plastic tanks a bad name. Finally, the designer must ensure these products are integrated and meet the quality and durability requirements of the stormwater management plan. So when specifying plastic tanks, there's a number of things to consider. Councils, through their development control plans, will enforce compliance to regulations. They will specify the methods and engineering needs to ensure the property meets the stormwater management plan. This takes into account the volume of water that the property needs to manage from landscaped, hardstand, and roofed areas. Not only does the certifying engineer need to integrate the tanks properly, but as with all key stormwater products, the structures themselves need to meet minimum strength, durability, and quality requirements. In Australia, there are no standards that govern plastic tanks, and the problem with that is that some manufacturers make claims about strength and design life that just aren't substantiated. However, there is a UK standard for plastic tanks called Structural Design of Modular Geocellular Tanks. It gives guidance on testing, structural design, construction, and installation. This is the gold standard to benchmark for performance, and as such, manufacturers should qualify their products to this standard and to ensure that failures don't occur. A structural design should consider the load-bearing capacity of the tank. The stronger the tank, the shallower it can be buried, resulting in reduced construction cost. What determines the depth of cover required are things like the soil type, tank design capacity, groundwater level, pavement thickness, and design loads. The UK standard identifies these being the main factors overlooked that contribute to failures. And manufacturers must be able to come clean on their strength data and prove it with independent testing. To address all this, the UK standard has detailed all the requirements for laboratory strength testing. And when considering loads, both short-term and long-term loads must be addressed. Dead loads include the mass of soil surrounding the structure, plus the weight of slabs, or anything else permanent that a tank will be subjected to. Live loads are temporary loads like vehicles, which also need to be considered. Tanks that have vertically aligned load-bearing pillars will offer good vertical strength and stability, and manufacturers should be able to provide you with independently tested vertical load results. Lateral loading is as important as vertical loading and takes into consideration soil mechanics. This is the key driver to how deep a tank can be installed. Beware that specifically in high water table application, tanks can be pushed out of the ground. So in these instances, either locate the tank close to the surface to avoid the water table or beneath a heavy pavement to anchor it down. Great emphasis should be placed on jointing methods. Systems that use a combination of brick bonding and cross bonding allow for a more rigid tank construction. Again, manufacturers should provide independently tested and certified lateral load data. This is to justify the installation depths they recommend for your project. Some manufacturers have a tendency to only disclose their short-term and not the long-term test results of their tanks. Products need to be able to sustainably support loads over the design life of the project. This is crucial for a durable installation. Tank materials are liable to creep, meaning that they deform over time, and products must be strong enough to withstand this. The long-term strength test data allow manufacturers to determine the design life of their tanks. Not appreciating long-term strength can have extreme consequences. This is an example of an installation where the tank has failed because of creep. It's really everyone's nightmare and just highlights the importance of long-term strength. Here's another, not a sinkhole, but an actual tank failure in Pittsburgh, Pennsylvania. Taking a tank out of a controlled environment like a laboratory and measuring behaviour in a typical environment gives all stakeholders a better indication of performance. Whilst the UK standard provides methodology behind laboratory static tests, ACCO conducted a full-scale live load test on a buried tank to an American standard. This was documented by Ohio University. Equipped with sensors to measure vertical deflection and lateral movement, the tank was installed as it would be in practice. Here is a short video of the test. This video and the test report is available on ACCO's website at accostormbricks.com.au. As there are no Australian standards governing the strength of plastic underground stormwater tank systems, we've teamed up with Engineers Australia to detail everything you need to know on the topic. This is so you can integrate tanks into a project properly without the risk of tank failures from either short-term dynamic or long-term dead loads. If the web address on the screen is too long for you to write down, it'll be sent to you after the webinar. For tanks, the hydraulic capacity refers directly to the volume of water that the structure can store, and different tanks in the industry will of course offer different capacities. You can optimize the capacity of the tank by selecting products with high void ratios, which is over 90% for geocellular systems. Having such a high void ratio reduces excavation and obviously the construction cost because of that. Now, arch systems, just for a quick comparison, with geocellular systems have a void ratio of around 50%, which essentially means the excavation needs to be almost twice the size. Arches hold water in the open space beneath them, as well as in the voids between the stones. This isn't an efficient way to hold water, not to mention the additional cost of the stone fill. On the screen is an example of two tanks side by side offering the same storage, and you can see the installation volume of the geocellular tank on the right is considerably smaller. Let's look at concrete structures. Although concrete tanks provide 100% water storage inside the tank, they do have thick walls which reduces the void ratio to around 80%, and they are very expensive to build and install. In comparison, geocellular tanks are more economical whilst still providing a high amount of storage. For concrete pipes, they are obviously round, but need a square trench. Each pipe needs about 250 millimeters of sand or stone bedding and around half a meter spacing between each run. All of this increases the excavation and fill required, making the installation bigger and more expensive. A good manufacturer should be able to help you optimize the space to meet the site's storage volume requirements. A tank versatile enough to shape itself around your project will give you more options to meet a site's storage requirements. Modular tanks offer the ability to adapt themselves to an underground space with some level of flexibility. This is particularly useful when avoiding things like existing services, buildings, or footings. Manufacturers should give you tank layouts to help you navigate the physical constraints of your project, as well as clear installation instructions. As I mentioned earlier, tanks can perform any or a combination of these roles, and depending on how a tank is used, it requires a different type of wrapping. In non-sensitive retention or detention applications, geomembranes are used as the bladder for storing water, along with a geotextile on the outside to protect it. Now, as long as minor leakages from the tank can be tolerated, the membrane is normally just taped together. This is used in the vast majority of applications. But for sensitive applications, like a tank positioned close to a building or simply contain contaminated runoff, we'd recommend using a welded geomembrane installed by an accredited contractor. This ensures watertightness, but as before, the geotextile wrapping on the outside needs only tape to secure it. The focus is on the integrity of the membrane. And for infiltration systems, there's no impermeable geomembrane used, just a geotextile which acts to minimize the sediment buildup within the tank while allowing for the water to percolate. Stormwater tanks can be very large, and moving them to site and then into the excavation can be costly. Geocellular plastic tanks are lightweight to transport, and the modules are designed to stack inside one another, which means they take up significantly less space than other products. This leads to fewer trucks to site and fewer trips to the excavation. Not only is this more cost effective, but better for the environment. The site itself should be considered when selecting a product. The time it takes to store and assemble these tanks can significantly affect construction costs. Some tanks need storage, and worse still, some tanks simply don't stack. Some plastic crate systems are generally assembled away from the excavation, then lowered in. There are additional rent and labour costs associated with building and storing the tanks before installation. Geocellular stackable tanks, however, are really beneficial for sites with restricted space or labour, in that they can be built inside the excavation. So, to get access to a tank, a dedicated entry point for both inspection and cleaning is needed, like the inspection chamber shown on the top right. For inspection and maintenance, open cellular tanks provide uninterrupted access from one cell to the next. This is in stark contrast to the closed-in structures of traditional crate systems. A tank that can't be maintained serves no purpose. Cameras and jets must be allowed to pass throughout without restriction. Here is a short video of an inspection carried out in a modern geocellular tank design. A geocellular tank is located under a pedestrian precinct. A maintenance team has lowered a camera down a shaft through the inspection opening. You can see the camera move through the system easily without being restricted by any physical barriers in the tank. At the bottom right, you'll notice a chainage counter showing the distance travelled by the camera cable from the manhole. If I showed you the full video, the camera ends up 30 metres into the tank. This would not be at all possible in tanks constructed of plastic crates. And so we've now come to the end of our presentation. But to summarise, these are the key things to consider when specifying tanks: compliance and legislation, the tank's design and strength, the void ratios for storage, how easy it is to transport, and the ease of access for inspection and maintenance. This now ends the formal part of our presentation. A little bit about ACCO. These are our products for external applications. We offer trench drains designed for buildings, urban and civil infrastructure projects. ACCO Access is our range of access covers, and ACCO CableMate is our range of cable pits. Our own geocellular tank is called Stormbricks. We have two versions, SD for vehicles up to 9 tonnes and HD up to 30 tonnes. Details of this product range can be found on our website. These systems can be incorporated into water-sensitive urban designs using the Storm Updated program by Clean Stormwater or Music program by eWater. To help you manage surface water for your projects, whether it be to collect, clean, hold or reuse it, I'd like to say that we're here to help you across the board with all of our products. askacco.com.au is where you can find all of our free project services. These are designed to complement your own project-specific calculations. You can email us your project requirements or even ask a simple question to askacco@accoaus.com.au. Part of our suite of services is that we can help you with storage above ground or below ground. Where the consequences of ponding water on the surface are low, we can provide a ponding analysis when temporary ponding can be tolerated. We do this by deliberately undersizing trench drains to restrict flow. Alternatively, we can help you remove water entirely off the surface with adequately sized surface and subsurface drains. We have a technical team of engineers ready to assist you. For your specific projects, this involves us configuring both trench drains and tanks and providing you with a part schedule for that configuration. We can also provide structural tank calculations based on the UK standard structural design of modular geocellular tanks. We can provide you with a fully documented proposal specific to your project. This is a service offered free of charge and without obligation. To help you specify the correct size tank, we've designed a simple online Stormbricks configurator program. All you need to do is to provide some basic information such as your desired tank size or storage volume, cover depth over the tank, type and location of inlets and outlets, and the configurator does the rest. The results can be downloaded and provide a summary of the inputs and a bill of materials for the configured Stormbricks tank, which can be emailed to ACCO sales team for a price and availability. To make the structural validations process easier, we've also designed a simple online structural calculator. It's very simple to use, and the required inputs include cover depths, height of water table, live loads, pavement type, and soil type. The results can be downloaded as a 2-page summary or a 6-page comprehensive report. The Stormbricks Configurator and Stormbricks Structural Calculator are both available on ACCO's website for you to use any time of the day. If you would like to talk to us directly, we have technical representatives across the country who would be only too happy to assist you with your next project. Thank you so much for your attention today. I'll make sure our post-webinar email to you contains all the links necessary for you to learn more or simply reach out to us when you need to. I'll now hand you back to Amanda.
Thank you, Darren, for your presentation. I'd now like to welcome our second speaker, Mark Liebman. Mark, a chartered professional engineer, is a founding director of Sustainability Workshop with degrees in civil and environmental engineering, First Honours UTS, and Economics, Sydney. Mark has developed a strong standing in the industry and is a thought leader and innovator in the water and environment arena. Mark has over 20 years' experience, which has seen him working on projects in the Republic of Georgia, China, UK, and Australia. Over the last 20 years, Mark has helped to pioneer water-sensitive urban design in Australia, with specific fields of expertise in water quality, management, modelling and design of stormwater treatment trains. Mark's degree in economics is frequently used while working with councils and developers on integrated water cycle projects, economic analysis of projects, and development of responsive, scientifically sound policies and implementation tools. Please welcome Mark Liebman.
Good morning. Thanks very much for that introduction, Amanda. I begin today from Blackheath in the Upper Blue Mountains by acknowledging the Darug and Gundungurra people, traditional custodians of the land on which we meet today, and pay my respects to their elders past and present. I extend that respect to the Aboriginal and Torres Strait Islander peoples who are in the audience today. In acknowledging country, we must start by trying to understand the history of our respective countries and how fire management by First Nations people has shaped this landscape with its cool burns. I'm no expert in this space, and if you want to know more, please read Dark Emu by Bruce Pascoe, who is Professor of Indigenous Knowledge at UTS. I would like to acknowledge the New South Wales and Australian governments for providing disaster risk reduction funding, which was used to implement the disaster risk reduction measures, which I'm going to talk about today. So, an overview of the presentation today. Really the focus is on water resources for disaster risk reduction, and there is a very large focus on fire risk. So to put it into context, all of this work followed on from the 2019-2020 Black Summer bushfires in the Blue Mountains, which were quite significantly impacted. I'm going to talk about the Planetary Health Initiative and working on a joint grant with them, and we're going to talk about the solutions that we developed to increase resilience to disaster, specifically the resilience to bushfire risk. So the focus of the presentation is on the disaster risk reduction grant that we got. We're going to talk about an underground demonstration tank, bushfire sprinkler demonstration wall, and bushfire water spray system installation on the National Parks and Wildlife Service Fire Control Centre. We're going to look briefly at grey water reuse and black water reuse, which really come into their own in terms of hydrating the landscape. And we're going to look at bushfire water spray system design guide. So we just have to put the risk in context here, and risk communication is really critical in this space. none of the risk management measures that we are looking at today are intended to make people feel safe enough to stay instead of evacuating at the appropriate time. In fact, all of these measures are the risk management actions that are the highest hanging fruit. They're not the easiest things, they're the hardest things to do. And really people need to be encouraged to undertake the low hanging fruit. Things like managing an asset protection zone, sealing a building, replacing flammable materials with non-flammable, and so on. The evidence base for a lot of what we're going to present today is not very strong, and it's a pretty immature space, but it is growing rapidly. One of the key areas that I have found is really immature is with respect to remote operation of bushfire water spray systems, and we really need our electronics engineering brothers and sisters to come and innovate in this space. So this slide is going back to December 2019. It's from a lookout in Blackheath. It's looking north towards the Wollamai National Park and the Gospers mountain fire, which burnt out of control for more than 4 weeks. According to the Sydney Morning Herald, one bolt made ground near a disused airstrip at Gospers Mountain, a densely grown area of the Wollamai National Park. It prickled the kindling into life. It would become the epicenter of the biggest forest fire to have started from a single ignition point that Australia has ever known. This satellite image puts the scale of this fire into perspective. It was absolutely enormous. By the middle of December, this fire had actually burnt 66 kilometres and had reached Blackheath. On this day, we had some pretty crazy wind, and a backburn had gone wrong, and the backburn had inadvertently jumped into the Grace Valley and started its own fire, which then started to head towards Blackheath. This was the day I evacuated my family. Blackheath was eerie. Everyone was staying indoors or evacuating. The Indian Ocean dipole started to turn at Christmas, and by New Year's Eve, we had a sprinkle of rain and it started to get cold. On a perigee or supermoon weekend on the 10th of February, the drought broke with over 400 mil of rain falling in one weekend. It was a long duration, 24-hour, 1 in a 100-year event. Another weekend in March 2021, we had over 500 mil of rain falling. Suddenly, we went from managing fire risk to managing landslide risk and COVID risk, but that's another presentation for another day. So when the ash had started to settle and the vegetation had started to grow back, I started to think about solutions and resilience and what we could do to obviously increase our resilience. So resilience refers to the ability to successfully adapt to stresses, maintaining psychological well-being in the face of adversity. It's the ability to bounce back from difficult experiences. At the same time, I'd been working with Blue Mountain City Council on designing a new pipeline to replace an old failed stormwater pipeline at Blackheath Golf Course. The new pipeline would connect an extra 10 hectares of catchment to an existing dam that would be used as a source of water supply for aerial firefighting appliances. This was a great solution to both increase resilience and solve a drainage problem at the same time. I started to talk with a colleague, Liz Bastian, who had been employed by Blue Mountain City Council to develop the Planetary Health Initiative. We submitted a joint grant application for disaster risk reduction, and we were successful in getting that funding. Our grant application was to support the Planetary Health Initiative, which is really a learning organisation. It's a capacity building organisation, and its intent is to create systemic change. We wanted to increase not just the capacity of local designers and builders, but also local residents, local RFS, anybody that we could influence really. The grant was an interesting mix of technical and communications. Half the grant was spent building disaster risk reduction measures, while the other half was about communications. That is learning lessons from what people did and sharing those stories. We focused on both chronic risk, which is everyday risk, for example, drought, and also acute risk. Fire risk is an acute risk. We came to understand that by providing water resources to hydrate the landscape, we could potentially combat both types of risk. It's obvious that dry landscapes are more flammable, and there is scientific evidence for this. In the upper mountains, we have a lot of ridgetop development with very shallow sandy soils and weathered bedrock at about 1 to 1.5 meters below ground. We have a lot of dead-end streets, and water supply in these dead-end streets can be an issue during a bushfire emergency when water pressure can be very low. Our solution to this is to propose buried storage tanks at key locations to make large volumes of water available to RFS and Fire and Rescue New South Wales. We constructed a demonstration proof of concept underground tank at the Planetary Health Initiative. The idea behind the tank is to provide a static water supply in key locations where water resources are limited, avoiding the need for fire tankers and their crew to leave a fire to refill with water. I've had a recent conversation with a friend of mine who works with fire and rescue, and approximately half of the firefighting resources that are available at the time are not being used because they're travelling back to refill. Our demonstration tank is 150 kilolitres with size mainly driven by budget and space. The tank is connected to a bushfire water spray system on the Planetary Health Centre building, which also houses the National Parks and Wildlife Service Fire Control Centre. This is a pretty important building to protect. The source of water for the tank is the car park of the Planetary Health Precinct. We've placed 200 micron litter baskets filtering the flow. Essentially, this is a small stormwater harvesting project. We also designed a rising main to lift water up to the road so that 2 fire tankers at a time could come and fill up in about 3 to 4 minutes and then move on. The tank was built over winter, which was ironically very cold and very wet and quite tough for the team that were building it. The tank is constructed from Acco storm bricks, and the tank is only 900 mils deep. It had to be shallow to reflect the ridgetop context, where bedrock is about 1 to 1.5 meters below the ground. The tank was assembled in a few days. After excavation, it has a welded high-density polyethylene membrane wrapped in a geofabric to protect that membrane. It has drainage on the outside to combat buoyancy. This is the tank wrapped up, ready for its final welding. I've been specifying Acco products for many years for infiltration. I understood their structural characteristics from the time I'd spent in the UK, where geocellular products are used on most projects to help reduce flood risk. In the UK, through a group called the Construction Industry Research Association, specifications for geocellular structures are well advanced. Failure modes from short-term as well as long-term repetitive loads, otherwise known as creep, are recognised. Even though what we built at the Planetary Health Centre is not subject to repeated loading, we needed to make sure our proof of concept tank could withstand a typical repeated roadside loading. A creep failure of a tank under a road is not an affordable option for a local government. We worked with the University of Wollongong Sustainable Building Research Centre to do a building bushfire risk assessment on the Planetary Health Centre building, which is shown in the centre of that aerial image. We started with the low-hanging fruit, such as looking at seals, sealing of open vents, removing of flammable materials, and a range of other similar measures. We also included a demonstration of an external window sprinkler spray system as a way to manage a key fire risk to this building. 7 windows were to be protected with flat fan spray nozzles, each spraying around 30 litres per minute at 1.75 bar. Our design criteria came from AS 5414, which is a standard for bushfire water spray systems, and this required us to deliver 10 litres per square metre of window per minute, which is quite a substantial flow rate. We also built a demonstration sprinkler wall, which includes a range of sprinkler types, showcasing what's more effective and less effective. We'd become aware that a number of call them amateur bushfire water spray systems had been constructed, and that people were using fine aerosol nozzles, which we think would be quite ineffective during a bushfire. They can be useful for hydrating the landscape, but I would not like to rely on them to effectively cool a building or reduce fire risk. The Planetary Health Centre organised a bulk buy discount for supply of rainwater tanks, which has been very well received and used by the local community. We partnered with Sydney Water and have a demonstration hydroloop, which is a household scale grey water recycling system. This is important because it creates a way for household scale drought proofing and a way of hydrating the landscape to reduce drought and therefore to reduce fire risk. We've also been looking at opportunities for black water recycling. We think this is probably a huge opportunity because it's the only highly reliable source of water. If treated, it could be used to fill reservoirs and dams at key locations to make water available for aerial firefighting appliances. The optics of black water reuse are not great. There will be a lot of resistance, and itself, it is an extreme risk. And in terms of risk, it also should be considered as a way of transferring the risk. We're transforming fire risk into health and environmental risk, and obviously we need to manage all of those risks. It's probably a lot easier to manage the health and environmental risks than it is to manage the fire risks. We needed to look at the economics, considering real costs such as unaccounted for water during emergencies, which we know to be absolutely significant. Really, our objective with this was simply to get the idea of black water recycling back on the agenda because we know it's going to be required. We did a hypothetical study looking at an opportunity at the Planetary Health Centre. We were looking at attached growth treatment units, which I understand are much better than the most advanced forms of wastewater treatment, such as membrane bioreactors and polishing in artificial wetlands. And then we looked at topping up a storage, which would then be available for an aerial firefighting appliance. And elsewhere, we would be able to use that water to irrigate and hydrate the landscape and reduce the risk of fire approaching the Planetary Health Centre. One of the key things that we did was develop water spray guidelines, and that's for bushfire water spray systems. Again, we worked with the University of Wollongong, and the guidelines build on AS 5414, which I understand is currently being revised. AS 5414 is the relevant standard for bushfire water spray systems. Our intention was to provide a readily accessible guideline based on the best scientific knowledge that we could access. We've taken a lot of care with the way that we communicate the risk. We would definitely not want anyone staying behind to turn on a bushfire water spray system and then be unable to leave. We know of this exact scenario happening where somebody stayed and it was too late for them to leave and they got covered in foam when an aerial firefighting appliance had done an aerial drop on their property. We certainly need engineers to play a leading role in refining these systems. In particular, we really need to work with electronics engineers to develop remote activation for them. That's one of their key weaknesses at this point, but in the digital age that we live in, I'm pretty confident that we can come up with a good solution. The guidelines include the results of continuous fluid dynamic modelling from the University of Wollongong, which demonstrates the effectiveness of different types of sprinklers under different mounting locations and how they can be affected by strong, windy bushfire conditions. This work is intended to help designers understand how ineffective some systems can be and how important it is to have a diverse approach to spray systems and to understand local conditions, to really understand where, for example, that the key bushfire risks are coming from and where it's likely that you're going to get prevailing winds during those emergencies. So to try and wrap things up, some of the key learnings include that there's no one-size-fits-all solution. We need a really big tool bag of solutions here. We need to keep our landscape hydrated. We need emergency systems in place. I've also observed that we have a tendency to avoid complexity and to avoid integrating our water resources. However, if we are going to have any chance of really building resilience, we need to embrace complexity and we need to integrate all of our resources. We also need to have a really frank appraisal of risk. And by that, I'm specifically referring to appraising human health and environmental risk in the context of fire risk, and specifically with reference to blackwater reuse. I wanted to acknowledge the amazing work done by Blue Mountain City Council and leading in this space, and the Planetary Health Precinct and their recognition of the need for disaster risk reduction. Thanks also again to the New South Wales Government for their disaster risk reduction funding. Thank you.
Thank you. Thank you to our great speakers. It's now your turn to get involved, but before we move into the Q&A, we will be running a poll, encouraging you to get involved. So please scan the QR code on your screen or follow the link in the description box. The results will show on screen as you answer, and Darren will provide his comments when shown. So kicking off, our first question is, are you more likely to specify a tank if it comes complete with other products? Ranking 1 to 4, with 1 being the most common. With the options being 1, the tank on its own, no other products are required. Number 2, the tank combined with only an adjacent downstream flow control structure. Option 3, tank combined with only an adjacent upstream treatment device. And option 4, tank combined with both adjacent downstream flow control structure and upstream treatment device. So I'll give you 15 seconds to think about that. Okay, I think we've got most of our results in. Darren, your thoughts?
Oh, thanks everyone for participating in the poll. Yeah, look, we asked that question just to help us to understand, as for you designers, what you require. We supply some of the products, but we will look at, I suppose, R&D and developing other products that will complement our current products. So, looking at those results, it looks like the result is most will require both upstream and downstream, and yeah, that's pretty good feedback for us to have a look at our product range and what we can improve and offer to new designers in the future with different new products.
Thanks, Darren. Thank you for that. Next polling question. What are your key concerns when specifying tanks? Rank 1 to 4, 1 being the most common. 1, is there room to fit the tank without interfering with footings, services, etc.? Number 2, is the tank strong enough? 3, is the tank able to be maintained? And 4, is the tank economical to install? Thank you. So I think we've landed on our final overall result. Darren.
Yeah, interesting seeing those results. I can see that interference with slabs and footings was up there. I know that from looking at all these past projects that we've done, that limited space is most of the issues. And you're trying to fit a tank within the property where there's not much room to put that. So yeah, that is a great concern, especially in built-up environments. And also saw number 2 coming in as maintenance. Obviously, you need to be able to maintain your tank, otherwise it shortens the lifespan of the tank. And to keep it functional, it has to be maintained. So yeah, definitely, we will look at offering ways on how to clean the tank, looking at ways on how to improve our products to meet your requirements.
Thanks, Darren. And to our third and final question, thank you everyone for getting involved, is what support do you value the most from a tank manufacturer? Rank 1 to 5, 1 being the most common. Number 1, project-specific support to size and configure a tank. 2, project-specific structural calculations to verify a tank's strength. 3, personalised support from a technical representative for 2D and 3D drawings and product data sheets. And 5, BIM models. Thank you. Darren.
Yeah, looking at those results, we're always looking to improve our technical support services in any way we can. So we'll review all those answers and come up with ways, improve our ways of communicating information to you, helping and assisting you in your next project.
Thank you. Thank you for everyone for participating in that. It's a great way to get some real-time understanding of your thoughts and your input. We now move into the Q&A. So please ask our speakers questions via the YouTube chat box and who your question is directed to. And thank you to everyone who submitted some questions whilst registering. And we might start with one of those with you, Mark, that's come from Francis, asking any configurations that do not need a water treatment plant. Mark.
Yeah, thank you, Francis, for your question. It's a really good question. Whilst the Echo tanks have the capacity to be maintained, and that means that you can clean and remove sediment from those tanks, I think everyone would agree it's a lot easier to prevent sediment from getting into the tank in the first place. To that end, I would recommend that you either installed a gross pollutant trap. There's a number of very good proprietary products on the market that are capable of removing at least 50% of the total suspended sediment loading. Or you could use litter baskets. In the example at the Planetary Health Centre that you saw in my presentation, we've installed 200 micron litter baskets in all of the pits upstream of the tank, and that's the primary filtration and the primary way that we stop sediment from getting into those tanks. So look, you might want to think about whether you need a gross pollutant trap. If you're just collecting roof runoff, I can see that a simple sediment sump might be sufficient, but I would say that's the absolute bare minimum for roof drainage. Yeah, and for anything coming off the ground surface, I would say absolutely you need some kind of filtration there. Thank you.
Thank you, Mark. And moving on to you, Darren, we've had a question that's come in from Ian, and Ian's watching in WA. Good afternoon to you, or it could be still morning there. How are these underground systems cleaned and maintained? Darren.
Yeah, thanks, Ian, for your question. As you would have saw in my presentation, there was a video on how to clean, I suppose, Stormbricks tanks. Our Stormbricks tanks are pillar systems, so you can actually gain access to every corner of the tank, in between the pillars. And how you clean it is, you first of all, you'll have an access unit with an inspection opening. You can get access through there to drop in a camera. Camera can run up in between the pillars just to view how much sediment's inside the tank. And if you need to clean it out, then all it is, you just get a sucker truck with a vacuum pump and just put a high pressure hose in there just to disturb the sediment, and then make it all suspended, and then get the sucker truck to vacuum it all out. So that's the way to do it with our tank. Other tanks, depending on the designs, there's other tank designs out there using a crate system where you can't get access through the tank. You can really get access to maybe a column vertically down. If that gets clogged up, you've got no access to clean out the tank. So you really got to look at the design of the tanks that you specify and install. Some can be maintained very easily, some can't. So yeah, I suggest you to have a look at whatever tanks you will specify, that it is easily maintained and accessible.
Thank you for that, Darren. And Mark, we've had a question that's come in from Justus, who's watching in Queensland, asking, how much can we store underground? Thanks, Mark.
Thanks, Justus. Good question. Look, I think the answer is depends how much space you've got and how deep you can go. But effectively, you can store as much water as you want. I can't see, any limits to that other than budget and your actual site constraints. For me, where I live, typically we hit bedrock at about 1 to 1.5 meters below ground. That forms a pretty hard constraint or a hard limit for me in terms of how far I can go down. And it's going to be different all over Australia. So I think have a look at your site constraints. Thank you.
Yeah, look, I like to add to that. It really depends on the development too. In commercial developments, you got big hard stand areas. They're usually used to house these tanks to collect water for reuse or for detention. Under sports grounds, you can put a complete tank under a full 40 football field if you like to reuse. So yeah, it just really depends on what constraints you've got on site, what buildings are around, and exactly what's in the ground too, as Mark said.
Thank you, Darren. And back to you, Mark. A question again from WA from Glenn, asking, how do we keep water quality clean in underground tanks? Thanks, Mark.
Yeah, good day, Glenn. Another good question. And I think it's a really important question. So at the Planetary Health Centre, as I mentioned earlier, we've got 200 micron baskets that are filtering the stormwater runoff from that catchment. It's pulling out total suspended solids, but obviously won't remove any kind of dissolved nutrients or any other dissolved products at all. I think you need to look at what your intention is with that water. Often and by that I mean it's often not necessary to remove nutrients or dissolved products. For us, we're reusing that water in a bushfire spray system. It's critical that we have no or very little sediment in that water. That sediment will be largely removed by the litter baskets. It doesn't matter to us if we've got nutrients in that water or not. Yeah, look, there may be some situations where it does matter if you have nutrients in the water. Yeah, so I would think, in summary, what I've said already, you need at least to filter sediment out of the flow stream. Much easier to do it upstream of the tank than once it's settled out inside the tank. Number of really good, readily available products on the market. And I think really that's probably all you need, a really good filtration, good GPT upstream. Thank you.
Thank you. Thank you for that, Mark. Darren, we've had a question coming from Paul in Queensland asking you, on flat sites with limited downstream level control, how is detention being implemented when the detained volume is not free draining to an outlet? Pumping systems appear to be an operational issue that body corporates do not maintain over time. Darren.
Thanks, Paul, for the question. I suppose that's a challenge with all flat sites, with engineers trying to design how to connect into the stormwater network. Usually the stormwater network runs along the road in the council strip at a shallow depth, and you're trying to get your site, if it's a big site, trying to get the all from one end of the site all the way down to the other end. And in between, you'll have your pits, your GPTs, all the tanks, and then you need to get the water detained and then sent to the stormwater network. Now, I've seen some very clever designs in my time where these tanks are designed for dual purpose use, as in retention and detention, where you might install a very sizable tank under the driveway, and then have a very deep tank. Obviously, if you put the pipe at the bottom of the tank, you're not going to connect into the stormwater network because it's at a lot shallower installation. Where this is the case, you might use 2/3 of that tank height from the base up as your retention, and then have your orifice or your outflow pipe 1/3 of the way up, which is a lot shallower, which you can connect into the council stormwater network. So that allows you to have one tank for both purposes. Your retention tank, 2/3 of it will be filled with water, and once it reaches that level, you'll start becoming a detention tank as it fills up, and then the water will discharge out at a shallower height through the orifice into the stormwater network. So yeah, that's a very clever design I've seen that is very common now, used a lot, these dual purpose tanks.
Thank you for that, Darren. Mark, we've had a question that's come in from Subramian in New South Wales asking Mark, while we are retaining the stormwater, what are the losses which come in while storing long term? Thank you, Mark.
Thank you for that question. Look, the geomembrane that was installed on the tank, the demonstration tank at Katoomba, has got a permeability of 3 by 10 to the minus 14 meters per second, which is an incredibly small number. It's so small that I wouldn't even really bother trying to calculate what it translates to in terms of, millimeters per day. Just to put that number into perspective, a landfill liner, I think, has got to have a permeability of 1 by 10 to the minus 9 meters per second. And we're looking at a geomembrane with a permeability of 3 by 10 to the minus 14 meters per second. So very, very negligible losses through the liner itself. Look, it's quite possible that you will get some minor leakage through pipe penetrations through the geomembrane. That's a key area of risk when working with geomembranes. Look, we've got a pretty good standard detail for that, which involves clamping the liner around the pipe, as well as welding it and making sure it's really attached to that pipe so that doesn't become an area of weakness. Apart from that, really, you shouldn't get any losses at all. I would think that the quality of geomembranes being produced today is pretty amazing. There's companies like Global Synthetics out there that supplied our geomembrane. I'm sure there's plenty of others. We used a 1 mil membrane, which is quite flexible, and the flexibility of the membrane is important because it makes it a lot easier to work with and a lot easier to weld. Some of the thicker membranes, like 1.5 mil thick membrane, can be quite tough and quite difficult to work with. But really, you need to look at, I guess, the risk of leakage from the tank and just have a look at the context of your situation. Thank you.
Thank you for that. Darren, we've had a question that's come in from Lachlan, watching in New South Wales, asking you, some councils will not accept geocellular plastic tanks in lieu of concrete tanks. Generally, this is due to maintenance and long-term integrity concerns. Do you have any comments on this or examples where it has been accepted by a council as part of a residential development? Thank you.
Thanks, Lachlan. Look, some councils only accept concrete tanks and not accept geocellular plastic tanks. And as I alluded to in my presentation, the first generation plastic tanks that were more designed as crate systems where you couldn't really access and maintain, I suppose that limited the life of the product. And I suppose if you want an asset in a council area, you want it to be long lasting. I suppose that was one point that was not favourable in regards to plastic tanks, which it wasn't looked upon by the council. So with these other tanks that we, like the Stormbricks tank, we've learned our lessons from these first generation tanks that you couldn't be able to access and maintain, and we've designed a system with pillars that can be easily accessible and cleaned out. In regards to the strength of concrete tanks, these new second generation plastic tanks are a lot stronger now. They are designed and tested with many different short-term and long-term testing, lateral testing, to ensure that they will last a long time. So with councils, there are councils out there that are specifying these plastic tanks now. They understand they are improvement on the older generation. There have been a lot of installations by councils. We heard from Mark in his presentation that Blue Mountain City Council have accepted installation of Stormbricks. We've had installations new developments up in Newcastle, in New South Wales, also down in Mornington Peninsula, in the roadway drainage where the water is being collected off the road, and then it's actually piped into a tank that's in the council strip that infiltrates it back into the sands. So there's a lot of these little water-sensitive urban design strategies being used by councils to effectively let the water go back into the soils, infiltrating back in the soils. We've also had a installation in Bondi, down on Curlewa Street, where they actually had a curb drain, an ACO curb drain installed along the curb, collecting all the water into a pit, which directed it into a Stormbricks tank under the footpath. The footpath was actually installed with permeable paving too, so it actually absorbed a bit of the water during low rainfall into the permeable pavers, and then it actually soaked into the infiltration tank below, and then the infiltration tank will slowly disperse that into the sands under Bondi and back into the water table. So there are different councils that have accepted it. They've come up with all these sustainable designs, trying to treat water, and you'll still get the odd council that are still looking at concrete tanks as their go-to, but they're obviously looking at being a bit more conservative, going with concrete tanks. They're looking at other councils leading the way with these new plastic geocellular tank designs, implementations, and I suppose looking at the durability and longevity of these other installations. Other things to consider, I suppose, with concrete tanks, some councils have their setup of inspection and maintenance, so they've got all their confined space requirements for their personnel to get in there. They've got to check the CO2 of the tank before they go in, so they go in there and clean the tank out. But really, concrete tanks or stormwater tanks should not be cleaned that often anyway, because it's as some of the questions were asked before about treatment. It should be all treated upstream of the tank. These are a lot more easier and more cost effective for your maintenance crew to clean the GPTs and the filters instead of cleaning the tank itself. But tanks can be cleaned. Over time there might be a little bit of sediment build up in there, and then to make it workable and more efficient, you can clean those out. But you shouldn't be cleaning those tanks out anyway. If a GPT or the filtration systems upstream of it is regularly maintained. So I hope that
Thank you.
That question.
Absolutely. Thank you. Mark, we've had a question coming from Simon. Simon's asking you, Mark, what are the greatest obstacles to community adoption of blackwater reuse systems for drought mitigation and bushfire risk reduction? Thanks, Mark.
Thanks, Amanda. And thanks, Simon, for your really good question. I'm not entirely sure of the answer to this question. What I can say about this, Simon, is that it's not technology. We have had the technology for a very long time. Over 20 years ago, I've been working on projects in China where we're using membrane technology to recycle black water. That water was used for washing, not for drinking. There's places like Singapore where they recycle a small percentage of their black water and they drink it. I'm sure you're probably aware of what happened at Toowoomba, where there was a proposal to have a planned indirect potable recycling scheme. It got knocked on the head by the community pretty quickly. Yeah, look, in short, I think the answer to your question is coprophobia, which basically means fear of shit. And that's the community perception of Blackwater. I don't think people really understand the technology and just how advanced it is. Yeah, I think risk communication in that whole space is absolutely critical. You want to be very careful about how you word things and how well developed proposals are before anybody sees them. I think it's going to be a really interesting discussion in the future when the discussion turns to, shall we use recycled water to prevent bushfires and protect people and houses, or should we let a fire just rage through an area because we've got no water? And look, from my experience and my knowledge of two pretty severe droughts, the first drought was the Millennium Drought, where the inflows into Warragamba Dam in Sydney were pretty small and they were pretty bad. The next drought is what we experienced in 2018, 2019, and the inflows from that drought were, fractionally smaller, were significantly smaller than what happened in the Millennium Drought. And I'm no prophet. I can't tell you what's going to happen in the future, but if we're seeing a trend here of increasing droughts and increasing severity, then we are going to get to the point where we are really going to have to embrace this discussion wholeheartedly. I hope that answers your pretty challenging question. Thank you.
Thank you, Mark. A question that we have here from Lachlan. And Lachlan is asking you, Darren, can the geocellular systems be maintained by a typical residential homeowner? If costly maintenance contractors are required, I can't imagine council will be supportive. Darren.
Thanks, Lachlan. With the maintenance of a residential property, the tanks would be very small in regards to size, and there'll be probably the upstream treatment would be just a pit, maybe a trash basket. So as long as the homeowners they can manage, clearing out the trash basket from time to time, just to ensure it doesn't get clogged, or it doesn't let anything else into the tank. The tanks can be easily maintained. If it does get clogged up with things, not a plumber can easily go out there. Plumbers can, they've got the equipment. They've got cameras. They've got cameras that go into pipes. They can be also used in these tanks to see what's in the tank if it needs to be maintained. And then all it is just getting a pump into the tank and just sucking out all the water and all the sediment along with it, and then refilling it if it's for reuse. Otherwise, it's just left there for detention. So, in regards to cost, it's not too expensive. It's just like probably clearing out a pipe if it's blocked. You just get your plumber in to clear out any of the pipes leading in to the tank or leading out of the tank, and they can stick cameras into the tank to just to see if it's blocked or not. So yeah, it shouldn't be. It's just getting a plumber out to just check on your plumbing in your tank to see if everything's functioning correctly.
Thanks, Darren. Just staying with you for now, we've had a question from Christopher. Christopher's asking you, Darren, what options would you provide for tank storage and detention systems below the water table? Thanks, Darren.
Yeah, Christopher, that's a tricky one. For designers, obviously, if there's a high water table, what that tends to do with a tank, and if it's empty, it's trying to make the tank buoyant, so it's trying to push the tank out of the ground. So what we have designed here, we've using the UK standard, which looks at these sort of applications with high water tables is, how is the tank going to be anchored into the ground? So depending on how high the water table is, the higher it is up the tank, the more buoyant your tank is. So if it's too high, then it's too hard to hold down the tank. It could pop out of the ground because of all the pressures. Also, if it's a high water table, you're going to have a lot of lateral pressures too, from the hydrostatic pressure against the wall. Then that could affect the tank strength. So in regards to the tank specified, the manufacturer should provide information on tank strengths laterally. We can also help with our ACCO Stormbricks. We've got a structural calculator, which I discussed quickly at the end of my presentation, which is accessible on our website. It does take into consideration the buoyancy, so you can set up your tank with what cover you got over it, what the size of your tank in the ground. You can change the depths by the invert depths by putting in different cover over the top, and then you can put in where the water table is, and then our structural calculator can determine if laterally it's going to be strong enough, or if the water table is going to make the tank too buoyant and push it out of the ground, and it'll give you results on that. So yeah, I welcome everyone to come onto the ACCO website to trial our structural calculator and our configurator to design the volumes you need for your tank. The configurator can help, I suppose, sizing up your tank. You can easily just put in a volume that you require to be stored, and the tank can calculate that and give you a few different options, a few different depths and layer options on how deep or how wide or how length, and you can play around with that until you get a tank that can fit within your project requirements. So yeah, these two programs, the Stormbricks Configurator and Stormbricks Calculator, is available on our website 24 hours a day, so you can access it whenever you need to design and specify your project.
Thanks, Darren. And we're rapidly getting to the end of this Thought Leader session. So I would just like to invite Mark, starting with Mark and then Darren. We've covered a lot: underground stormwater storage for detention or reuse this afternoon. If you could just sum up really quickly the key takeouts from your presentation for our audience, starting with you, Mark. Thank you.
Yeah, look, I've been looking at underground storage tanks specifically for disaster risk reduction. We wanted to try the ACCO tank because it provides an opportunity to rapidly construct a tank at shallow depth with really good structural integrity. We could potentially put that in a road, although we're yet to try doing that. We've looked at a number of different ways of integrating the water cycle so that we can further reduce disaster risk reduction. It's a pretty immature space. We need some good innovation in that space. We certainly need some help from electronics engineers. Look, I think I've seen a lot of questions there looking at how long these systems are going to last, questions on how long the geofabric might last, and concern about whether you may get soil ingress into the tanks. Look, I've been looking at a number of different systems for over 2 decades, and I'm yet to actually see failed geofabric, especially if you use a quality geofabric. If you use the cheapest geofabric you can find, something that's not fit for purpose, that may well happen, and I would definitely stay away from those products. But otherwise, I don't really see it as a use. Yeah, we looked at membranes and wrapping tanks in membranes, and yeah, we've been doing that with bioretention systems where we have lined bioretention systems to retain water, and they work pretty well. So I can't see why it wouldn't work very well for tanks. Certainly the one we've tried is working pretty well. Yeah, I think that pretty much sums up my presentation. Thanks, Amanda.
Thank you, thank you. And Darren, we are rapidly running out of time, so if you could just keep it to 2 minutes max. Thank you.
Well, thanks everyone for attending today. Look, my key takeaways for you guys to take away from this presentation is, I suppose we've got underground geocellular tanks. The key considerations when designing tanks underground is you look at your legislations and your DA requirements for approval. And when selecting a tank or type of tank to specify, you look at the ensure the manufacturers provide all the strength test requirements, and also provide assistance with you sizing up the tank, with providing volumes and what the tank can do, and provide a tank that is very cost effective, that can be easily installed, lightweight and easily assembled on site, and for the asset owner, that can be easily maintained and accessed. That is the key. That's always been the downfall with tanks, but if they can be easily maintained and accessed, that'll go a long way for a long-lasting, durable solution. So look, with ACO Stormbricks products, we sort of hopefully tick all those boxes, and we look forward to you coming to us for any technical support, and hopefully you'll be successful in your next project.
Wonderful. Thank you, Darren, and thank you, Mark, for your great presentations and giving up your time today. Before we wrap up, I'd like to share a competition question from ACO. Please share your answers to the email on the screen and in the description box below. So, in 200 words or less, underground stormwater tanks can be used for retention. Other than using retained water for firefighting, pick another possible application and outline some key considerations. I'd like to warmly thank Engineers Australia's industry partner ECHO for their support on today's webinar. As always, if you could take a couple of minutes to complete a short feedback form, which is linked in the description box below, to help us improve and plan future sessions. Thank you again for joining us, and I look forward to seeing you at our next Thought Leaders event. Thank you and good afternoon.